break, we stopped at the measurement of the EGT. And yes, I have to use more, of course, but we did not go that deep. Telephone. Go on. Interstage turbine temperature, not that important because mainly on older engines, so we don't have to take care here anyhow. Yeah. So if I would like, or if I decide as a manufacturer I need those ITT, then of course I have to place the same thermal couple we use, Chromel, Alumel, the same idea, but I have then an additional, where I put it, yeah? Engine thrust, yeah? Patience. Also this, we have two ways that thrust will be indicated in the cockpit, yeah? Of course, the real thrust you cannot measure on wing, yeah? Because then you don't have the device that you have on a test cell, for example, those little pressure tubes that once the engine.
One guy still can connect. Please check.
You cannot hear me, or?
No. Just one guy can connect. Please check. He is in lobby.
Oh. Yeah. Yeah, shall we wait or shall I continue?
Continue. Okay.
Okay. Most important is that at the end of our day here, I will make a wrap up of all things we have discussed. So there, I would suggest that he attends. Yeah, this is the most important thing. Good. So I continue slowly. Yeah. Now, so the other one, to display if the engine has reached or is able to provide the takeoff power, is the EPR. Yeah, this is the ratio from outgoing total pressure to incoming total pressure, because the difference is what happens in the engine. Yeah, we have a certain amount of mass that will be accelerated, so we enhance the total pressure, yeah, mainly by the kinetic energy of the PD, and this is also an indication. Yeah, let me check here. So it's a decision of the engine manufacturer, yeah, which way he goes. There are engines that display both. For example, the V25 engine for the A320 fleet. There you can swap from EPR to N1. But this is general. Disadvantage is when you measure the engine pressure ratio, here displayed the so-called P2 port, where we measure the pressure incoming or in the pressure of the air entering the engine. And this you can save when you just measure the N1. Yeah. Rolls-Royce also V25, as mentioned, engine pressure ratio. Yeah. Here display, yeah, as an example, EPR. Yeah, of course, it will also be displayed which is the best one. Takeoff go around is not that important for us here, but it's a way to indicate to the cockpit. So integrated engine pressure ratio, I got no idea about engine type. Yeah, here another one, and you will notice is still this P2. Sometimes it's called P7. Take the highest number, yeah, which is mentioned. Yeah, so this is a ratio, and this displays my engine pressure ratio. I go for N1. Makes more sense, of course. N2 system is the real engine, the core engine, but N1 again, yeah, provides the majority of the thrust, so it's also a nice indication. And oil quantity and oil pressure, those are the three indications that will display in the cockpit. Yeah, of course, not the oil consumption, that's not possible. Yeah, and nothing else. Yeah, those are the three displayed in the ECAP. Yeah, temperature, pressure, and quantity. So the old version was a so-called burden type here. Yeah, what was the idea? You have this tube here, burden tube type measurement. And if you apply pressure on this tube, yeah, the tube itself would like to straighten itself. And then you have to, yeah, the connection here with an indication. It's an old fashioned, but still working on older aircraft, smaller aircraft, whatever. They still use those burden type thing. But for us, it's not that important because I think you work more on more modern engines. Of course, burden tube, gear pinion, you may have it. There's several options. Yeah, if you have one engine, two engines, you can place all your engines or all indications. And one thing here, triple design, double design. There are too many options you have. We don't have to care about this. And this is a better example for the burden tube here. You have here a liquid in this tube, yeah, and here's a so-called transmitting fluid. And as soon as the pressure of the oil arises, it gives the pressure forward to the capsule here, and then this circuit here tries to straighten itself. Yeah, it goes like this. And then, what? Would you mind? Yeah, thank you. Except it's for me. Otherwise, raise your hand. I try to take care here, or write me something if you do not understand me or whatever. Otherwise, it's maybe better if you switch off your micros. Thank you. So, what else have we have? Pressure switches, just an example. Yeah, this is one thing here. Make it a little smaller. Maybe this is better. Yes. Yeah. So the modern, the new are to measure the pressure, especially here in our oil system. Yeah. Idea is, yes, it's spring loaded. Of course, this spring is special. Then you have here so-called contact shaft, and you have an electrical connection. Once here, yeah, the oil pressure arises, it pressures also, or gives the pressure to the diaphragm, and then the contact shaft will go up, and then you have an indication about the oil pressure. In order to have the right adjustment, yeah, you have here the adjustment ring or adjustment screw, and this is a way today, yeah, oil pressure will be indicated and measured. Yeah, of course, then you have finally the electrical connector goes into the ECU, and further on into the cockpit. Yeah. Temperature also important. Yeah, maximum temperature was about 220 degrees because on the synthetic oils, yeah, maximum 250 degrees allowed. Operation, yes, it's not that important for us here. Fuel flow, and again, yeah. Of course, cockpit needs to know or would like to know the fuel flow. It's got nothing to do with FADEC system. FADEC system, yeah, relies on the position of the fuel metering valve, yeah, provided via the LVDT. But cockpit needs to know how much fuel is used, what is the fuel on board, FOB. Not a nice indication here. Well, of course, it's, yeah. So how does it work? Fuel flow itself. This is a fuel filter differential pressure switch I mentioned. Yeah, as an indication if the fuel filter should be blocked. Of course, if it's blocked, there will be a deviation in the ingoing and outgoing pressure, and this is a delta pressure switch doing. For me, it's enough if you know it. Here, this is one important thing. Once the fuel flow transmitter, how does it report to the cockpit? Yeah, and please bear this in mind. I hope you can see it here. Yeah? I read it. A fuel flow indicator is electrically operated and may be a synchro. So the medium, the device providing the data, yeah, the measurement to the cockpit is a so-called synchro, not an LVDT, not an RVDT, it's a synchro, please. Yeah, keep this in your mind, please. So, fuel flow transmitter, it's got nothing to do with the EC. Quite important, nice to know. Yeah? How does it work? There's another here example. Yeah, here, this one here. Yeah. So what happens is the fuel itself, yeah, is used to indicate this. Fuel is coming in here. We put into a movement, yeah, by this impeller here. So the fuel is now turning and also gives this force to this reaction turbine. And the reaction turbine now tends to turn also. And there's a restraining spring that works against the turning of the turbine. So this resistance will be measured and then displayed in the cockpit. It's not detailed enough, yeah? But it's okay for the pilots. Engine speed measurement, N1, N2, or if I have a Rolls-Royce engine, we have N3.2. Also here we have several different kinds of measurement. I go to the normal or the most used ones. What we try to do is where we place it comes later. Yeah. What is the idea? Where is it? Mostly it's a reluctance type measurement. Yeah. So we have a magnetic field here. Yeah. In this case. So, and we need something that turns because we would like to measure the RPM of a shaft. So in order how to make this, we need the so-called gear wheel here, but officially it's not called gear wheel, it's called a phonic wheel. Because if you have here a magnetic field and something is passing the field, is interrupting the field, all you have to do is to count the interruptions. Therefore, we need the so-called phonic wheel. So every gear here that passes through is detected, and then you have an indication for the RPM. This is the idea how this works. You may also use the fan blades. Yeah, in your fleet, you will probably have a CF6-80C engines. And as far as I can remember, GE decided to measure how to measure the N1, and they used the fan blades. So the pickup, the speed pickup is placed on the fan case. And then whenever a fan blade passes the magnetic field, this will be detected. And then you have a display on the N1. Yeah? N2 is quite simpler, or it's much more simpler because they use mainly the permanent magnet alternator, which provides the electrical power for the EEC and ECU. And it's directly related to the RPM of the N2 system. So they placed, or they use mainly the PMA for this. There's one exemption, the PW11 engine. It's got also a little phonic wheel on the shaft to the angle gearbox, but those are the two main items. Yeah, you can use the PMA or the fan shaft itself, the N1 fan shaft, or my fan blades. Vibration also very important. Yeah, because if I do not track the vibration of my engine, it may happen or escalate to the distortion of the engine, because at those speeds of the RPM, and including the weights, if you have an imbalance, yeah, that may cause this distortion of my bearings. Yeah, so we have a vibration pickup, and the example I take here is we have a two-shaft system. That means we measure on two places. What I do need is I need the pickup itself. Yeah, it detects the acceleration. Therefore, often we use the wording accelerometer. Yeah, then we have to amplify the measurement, and of course, then we have an indication in our systems. Yeah, mostly used piezoelectric crystal. Yeah, which if you apply pressure, those guys who smoke, yeah, our lighters have the same principle. Yeah, we have this crystal inside, and then vibration is nothing else than acceleration, and then the crystal will be put under pressure and causing a slight tension. And all you have to do is, yeah, to amplify this tension measured here this way, goes to the amplifier and then to the amplificator. Very important also. Vibration. So principal, operation, indicator, power supply, let me put here. Torque measurement. We skip this. Okay, no, just one hint. Yeah. Where do we find the torque measurement? Of course, on engines that just have the task to provide torque. Yeah, no thrust by an accelerated gas. So helicopters, helicopter engines, and APUs, for example. Yeah. Yes, also for turboprop engines. No, for propeller turbo. Yes, where we have also to measure the shaft horsepower. But we pick it here. Torque. starting ignition. Looks strange, but okay. This is what you have probably done also. Yeah, when after an engine change, of course, you have to make sure that the engine is working and properly working. Maybe make a maximum power assurance. So we go also to the start sequence. Yeah. Start sequence itself, in general, yeah, also guided, done by the EEC or ECU, or let's call it FADEC. Yeah. We stay rough here. A normal guess or a normal start sequence, how it should be. Yeah. In general, please bear in mind what comes first here. First, we have ignition on, very important. Yeah. Then we have, sorry. Yeah, so we have a starter who starts our system. Then comes the high pressure fuel. No, sorry, again. The starter starts to turn the N2 system. Then I have ignition on. After this, I have fuel flow. Yeah, this is a sequence. The starter starts to turn, then I have ignition and then fuel flow. You know this. Yeah? So we go through this here. So pilot, yeah, it's initiating the start sequence. FADEC does overtake, and FADEC does now open the starter valve because the starter is some kind of stupid. The two options: the starter gets pressurized air or gets not pressurized air. So all the FADEC has to do now, yeah. So three sources where pressurized air comes from are the APU, the ground power unit, or the other engine, which is already running. Yeah, and we talk about just air starters here. What happens, or in best case, now starting sequence is initiated, the ECU will open the starter valve, so pressurized air comes to my air starter and starts to turn the starter. The starter is attached to the gearbox, which is in most cases on a two-shaft engine or three-shaft engine. attached to the high pressure system, the real core engine. Now, please keep this in mind. The starter drives the high pressure system. Yeah. Starts now to drive the starter. Sorry, my voice is gone. The high pressure system. At the same time, also please do not forget the valves at the HPC bleed valves are open at this time to make it easier for the starter to turn the rotor, to enhance the rotor speed. If those HPC bleed valves would be closed, it's much harder for the starter to gain the necessary RPM. Yeah. So HPC blade is still open. Yeah. Now we have the high pressure fuel. In best case, we have a light up about somewhere between 5 and 10 seconds. So now we have a flame on. So the N2 system also produces some kind of thrust, and accelerated gas. The starter still supports the N2 system. Yeah. And then the next step here, about between 15 and 20 seconds. Yeah. The N2 system will reach its self-sustaining speed. From this, in theory, from this moment on, the N2 system should be able to work from alone without the support of the starter. In order to be on the safe side, the starter still helps a little bit, until this moment here, when the connection from the starter to the N2 system will be interrupted. It's quite easy. As soon as FADEC realizes, we are on the safe side, let's call it this way, the starter valve will be closed, so the air starter is not supported by pressurized air anymore. And then we have the disconnection via those flea weight principle. Now, because when the starter is not supported anymore, the gearbox turns faster than the starter. And then you have the disengagement clutch. It works mainly with the flea weights. And so we avoid that the starter is still turned with the N2 system. That would destroy the starter for a long time. In best case now, we have a little here, high peak of the EGT. Why? This is quite normal. Fuel and the air that is mixed with fuel is always present. That's not a big problem. But we have also to consider the 75% of fuel to protect the combustion chamber and also the turbo. So therefore, at the beginning, the EGT has a little peak, and then with enhancement of the RPM, also the protecting air, the cool air, comes later on, and then EGT goes down, slightly down, as mentioned here, little peak, and then goes down again. This is a normal starting sequence. Shouldn't last more than 30 seconds, and then it should be done. But of course, there are some mistakes that can happen. Those are mentioned on the next slide, the failures. And you need to know the 3 different kinds of failures here. We have a hot start, we have the hung start, and we have the wet start. Oh, sorry. Just for a moment. Someone is ringing at the door. So, sorry, the postman brings a package. So, 3 different kinds of starting failures or wrong starts, whatever. And it's mainly self-explaining. Hot start. Yeah. What is hot start? Of course, if I exceed the EGT, yeah, with more than it's limited. Yeah. Then we have the hung start. It's also can go back here. This is here an example for a hung start. Yeah. Although the N2 system reached its self-sustaining speed and the starter, yeah, will be disconnected, the system is not able to enhance the RPM further on. Yeah, it's maybe not enough support or in front of for the starter, or something miscalculated. Let me check here. So some miscalculation in the system, mainly the reason. And the last one here is the so-called wet start. Yeah, that's quite simple. You have a fuel flow indicated in this system, but you have no AGT arising. So that means you have no flame on. And then, of course, the combustion chamber is mainly drained with fuel, whatever, but it's a wet start. So no rising of the EGT. Hot start, hung start, and wet start. That's what you're supposed to know, but you know this already. So how does it look like here? Introduction, quite simple. Yes. How often do you do this engine checks? So I think many of you have a lot of experience in engine checks after assembly or engine change or swap. Does this happen very often?
Yes.
Wrong starts? Yeah, really? Why? Start. Yeah. Okay. Control. Yes. Oh. So. Okay. Oh, now we're completed again. Okay. So, are you ready for a wrap up? Electrical starter, air starter. We don't have to talk about this because you know this already. And I think if you remember when I was there at your facility, I showed you the little YouTube videos from the pilots. Yeah, how you can see. I think we have seen the hung start, and I showed you already in real the hot start where the EGT was reached and overdone. But I think you have enough experience regarding starting. Yeah, so it should work out fine. Ignition systems, yeah, this is nearly the last one here. Yeah, I need 3 devices. Of course, I need my igniter boxes. So the ignition system consists of 3 devices. I've got my igniter boxes, which are mainly used here. I mentioned it here. Is it capacitor type? Yeah, because we go in with a very low voltage and must convert in a high voltage, depending where we read. Sometimes it's mentioned 2000 volts, or some other handouts you can reach or read 25,000 volts. It also has, of course, to do with the amperes. And we have our igniter plugs itself. Yeah, beware when you install some. Yeah, the position, the depth, yeah, of the igniter plug is important. Not too close to the case, and not too deep into the combustion chamber. And where are my ignition LEDs? Not mentioned here. Okay, yeah, and then. Finally, here also starting ignition. Yeah, here the starter duty time is mentioned. The starter duty time describes how often a starter, in case of failures, may be used in a sequence. Sure, we have to read the manual because it may vary. The disadvantage of the starters, or majority of starters, is yes, they have oil inside, but they have no oil cooling system. So once you have a failure, starting failure, maybe 2, 3 hung starts, whatever, we have to give the starter time to cool down. And yes, please read the manual. That's what you do anyhow. And then you can find out what is a starter duty time. Safety requirements for ignition systems. This is just please read the manual. That you know better than I do. Okay. So, are you still there?
Yes.
Shall I start with sorry, that we make a wrap up here of the complete thing?
Yes, of course.
Yes. Okay. Stop here. We don't need anymore. It should be gone. Now you should see me a little bit bigger then. I'm sorry. So, conclusion of this here is what you already know. So, physical roots. I stated that the two most important ones. Again, the one that is describing how we gain thrust is is Newton's third law: action, reaction. The action is we accelerate a certain mass of air in one direction. What we would like to gain is a reaction, because then we move forward. So this is the most important thing related to how we build thrust. Thrust is a force, and there we know the second law of Mr. Newton. What is force? F equals mass multiplied with acceleration. When is this important? For example, when I would like to compare a newer high bypass engine with a pure jet engine, and both should reach the same thrust, because it's an equation and was multiplied, you can easily come to the conclusion that if the pure jet engine should gain the same thrust, the mass, it cannot move that much mass. So in order to gain the same thrust, it has to enhance the acceleration. Quite simple. So then we stay in general. An engine is roughly divided in two sections. Again, sorry. Need some liquid. The so-called cold section and the hot section. And you will hopefully remember where the hot section starts. It ends at the compressor, regardless if I have 1, 2, or 3 compressors. The cold section ends at the compressor, and so the hot section begins at the combustion chamber, including the turbines and the exhaust. Sorry again. Boy, what is this? Then what we have discussed is the different engine types, depending on the where I have to use it. Bigger aircrafts, we have just engines that accelerate a certain mass of air, but there are other engine types. For example, we have those APUs or helicopter engines. And we do not have any interest there in accelerated gas. So we have an interest that those engines have to provide torque horsepower. Or shaft horsepower, please. Bear this in your mind. Turboprop are between, because yes, the majority of turboprop engines, they produce torque, but there's also some remaining thrust produced by the exhaust. It's about 10%. And in order also to consider those additional thrust, they created the abbreviation ESHP, equivalent shaft horsepower, but this is only for turboprop engines. Coming to turboprop engines, in comparison with our high bypass engines, the advantages are they have more fuel efficiency. They have a better ratio of the cold and hot air. And since they are mainly disconnected, so they have a free LPT or a free shaft system, the engine itself, the gas turbine, can turn in its best RPM. Yeah, it's called the design point. The best RPM means, yeah, now you have a certain flow of the fuel fluid of the gas. You have a certain RPM and everything works perfect together. That leads to a longer time on wing. So this engine, turboprop engines, yeah, have a bigger gap regarding when is the next overhaul. Yeah. Advantages, turboprop engine. Fuel efficiency, they last longer on wing, and also, let me check. Yeah, better power ratio, for example, yeah, and they have a lower weight. Yeah, they are not that big, so a little bit more mass. Also, please consider they have an A380 lifts up with 4 bigger engines. The engines, the weight of the engine itself need to be lifted up. This is a disadvantage, or this is the advantage of a turboprop engine. Yeah. So then I talked about compressors, very important because the task of the compressor is to provide potential energy. Yeah, we have several or 2 kinds of compressors built, radial and axial. Every compressor type has its disadvantages and advantages. We find mainly on the bigger engines axial compressors because they consume the air we need. Radial compressors are limited in the consumption of air, regardless or depending where you read, maybe 60 to maximum 100 kilos a second. And with an axial compressor, you can consume much more. Yeah? Radial compressors are used if you need a small gas turbine. If you do not have that much space. For example, APUs mainly use just radial compressors, helicopter engines, yeah, the combination of axial with radial compressors, and our bigger engines only only axial compressors. Yeah? And also here, compressors and air, yeah, we have to take care. The design must be well calculated so we do not go the risk of a compressor stall. The compressor is very sensitive to stall, not the turbine. It is the compressor thing. And stall is influenced by 2 speeds, the speed of the RPM of the rotor and the speed of the gas or the air, yeah, hitting now my rotor. What we do is, or what they have to do constructional wise to avoid stall, you have multiple shafts, therefore they could build, yeah, the bigger compressors. Then we have our 2.5 bleed, so right after the low pressure compressor, we have to get rid of some air in order not to put too much air into the high pressure compressor, which he cannot consume. Then we have our VIGVs, variable inlet guide vanes. Then we have variable guide vanes to make sure, yeah, that the air is constantly flowing, yeah, through my compressors. So another thing that could be done, but it's on older engines, in order to control the airflow through the compressor, is that you maintain a certain blade clearance, the adjustment of the blade clearance. I know older engines where they heated up the compressor rotor in order to optimize the blade clearance. You remember what they do on what they do on the low pressure and the high pressure turbine, where we have our so-called active clearance control. It's the same idea to enhance the performance of the module itself or the section, where they shrink down the case at a certain moment in order to have a better clearance. Yeah, mainly used in cruise. Then that makes more sense. Yeah. Please bear in mind how we control air through the compressor, VIGVs, VGV, and maybe adjustment of the clearance. Yeah. Also, especially at start, we have to help the compressor, especially the high pressure compressor, to avoid stall, and we have also our bleed valves here. Regardless if it's the bleed valves behind the low pressure compressor or the HPC bleed valves. Yeah? In general, yeah, we try to protect the compressor with those bleed valves. Yeah. Okay. This is also very important. Then we talked about FADEC. So FADEC was a system that gives the engine the full authority about himself. Of course, FADEC has to obey to the cockpit, to the wishes of the cockpit. But if the pilot makes a wish, yeah, or orders more for maybe takeoff power, yeah. First of all, the FADEC system will take care about itself. Yeah, so the engine will take care about itself. That means he received the order, please take off, yeah, or enhance the thrust to takeoff thrust. But the engine will first check, yeah, what is my condition? What are my RPMs? What is my EGT? What is my current fuel flow? In order not to enhance the fuel flow too fast to destroy the engine. There must be always a gap, yeah, a distance to the so-called stall and surge line. Yeah, bear this in mind. Yeah, of course, the FADEC system will enhance the fuel flow, but not without touching this special line. And also, again, idea is to enhance the fuel flow to gain the takeoff thrust. So the system considers N1, yeah, because N1 is a goal that he has to reach. Yeah, so the system will say, okay, now I will enhance the fuel flow in accordance to N1 without touching my stall surge line. Yeah, very important. So, and how does a FADEC know that the pilot's now wishing that he requested the takeoff thrust? Normally, he presses the takeoff mode button, or he pushes the thrust levers. Yeah, now is different. To take off or beyond takeoff. I want you to recognize or remember that it's there. The thrust levers have to be beyond the thrust takeoff position. Also very important that the FADEC will make the measurement or the feedback signal from the fuel metering valve, not from the fuel flow transmitter. Yeah, the position of the fuel metering valve is more detailed, it's more exact than the measurement from the fuel flow meter. And therefore, there must be communication. And the fuel metering valve communicates back to the ECU via an LVDT. And in general, yeah, when you compare the FedEx system with a human body, let's say it this way, ECU is my brain, I need someone else. Yeah, I need harnesses, signals to someone who transfers now, yeah, the idea, the order to movement, mechanical movement. And those are mainly torque motors. Yeah, you can, let's say torque motors. Someone has to transfer, yeah, a thought, an order into a movement mechanically. And this is a so-called torque motor. We discuss this too. Yeah? So, yeah. Then we talk about, yeah, engine thrust ratings. As in safety, as in redundancy, therefore, I think you know this better than I do. Yeah. What you please bear in your mind is, if the thrust rating mode, yeah, does not agree as or react as the FedEx system expects, the FedEx will automatically go in takeoff mode. Please bear this in mind. Yeah. So you got my point? It's hard to describe in other words. Yes. Yeah. Okay. Good. So this is for me. It's okay. Yeah. That you go here maximum takeoff mode in case that the system, yeah, that the thrust rating modes do not are in line or react in a certain interval as the FedEx expects. Let's say it this way. Yeah. Then we had some talk about some indications. One of the most important one is the EGT. The exhaust gas temperature indicates the performance of the engine, and also if I'm shortly before destroying my engine, please bear in mind, first task of the turbine is to survive with these temperatures. So, and then they invented, yeah, the so-called thermocouples. I call them thermocouples. Yeah, we have two metals, a bimetal. The idea is quite simple. As soon as those chromel, alumel, yeah, thermocouples heat up, they produce a certain voltage, millivoltage, yes, yeah, and there's a ratio about 100 degrees, about 4 millivolts for they produce. All you have to do now is to collect those millivoltages, amplify it, and then you can report to the system and also to the cockpit. Yeah. Since now chromel, alumel, chromel is plus, alumel is minus, produce their own electrical power, they do not need an external electrical power. Quite simple. In order to make the system working, even if a thermocouple fails, you have to put them, yeah, the circuit needs to be in parallel. Otherwise, would it be in series and one fails, you have no indication. Yeah. And another one we talked about EGT was, let me think, I know power supply. Oh yeah, if it comes to maintenance, yeah. Of course, those thermocouples are connected via wiring. If you should be in a position to replace those wiring, you have to consider to use the same material as normal. I know it sounds stupid, yeah, but because you will use the same. You look into a manual IPC, whatever, yeah. But if you don't do this, yeah, it may have an effect about the measurement and the result. Yeah, because you have another material and that has maybe another resistance, internal resistance, and then this could lead to a failure in the measurement. Yeah? So take this please also in consideration. Yeah. Another thing I told you is here coming back to the fuel flow transmitter. Yeah, of course, pilot needs to know and how this signal will be. I think it was here. Yeah, how this signal will be transferred to the cockpit, and it's not an LVDT. It's also not a torque motor. It's a synchro. Yeah, it's provided, transferred via a synchro to the cockpit. Yeah. And when do I measure the fuel flow? When do I measure the fuel flow to the fuel nozzles? What would make more sense as per your perspective? The problem is when we take a look, or you have the fuel system in your mind, and you know there's a low pressure pump, there's the heater is up there, fuel or heat exchanger. Then we have filters, a low pressure filter, maybe high pressure filter. If it comes to that, you have to think about when you measure the fuel flow, please take the one that is the closest to the fuel flow transmitter. You get my point? Yeah, let's say it this way. Maybe your grandma asked you the question, when do you measure the fuel flow? And you hear after the low pressure filter, after the high pressure filter, or after the high pressure pump. Take this, what is closer to the fuel flow transmitter. Officially, yeah, it is right after the fuel metering valve, or when the fuel gets out of the HMU, yes, yeah. But maybe you find three options. Oh, let's say it this way. If all three options do fit, are reasonable, take the option which is closer to the fuel flow transmitter. You understand so far? Yes.
Yeah.
Yes. Yeah. I'm sorry, I cannot describe it another way. It's some kind of, yeah, what can I say? Yeah. So what else? Yeah. We talked about indications, additional indications to the cockpit, which was regarding fuel, for example, oil, oil temperature, oil quantity, and oil pressure. Yeah. Of course, we have also our vibration indications. If we have a two-shaft system, we measure, normally at the fan case and at the turbine case, turbine rear case, depending on the OEM. So we measure here too. And it's mainly use the principle of the piezo crystal, which is once under pressure, it causes some tension, and this will be collected and amplified, and then reported also to the system. Yeah. So what else? We talk about the starts. We use an air starter mainly. The air starter is some kind of stupid because it's not regulated whether it gets compressed air or not. So the FADEC will initiate this just by opening the starter valve, and then the starter will be turned. Yeah, the pressurized air reaching a turbine and then a reduction gear. And by doing this, now we have a turbine turning the gearbox. Please don't forget that the starter is turning the high pressure system if you have a two-shaft system. If you have just pure one on one shaft, the question will not arise. Yeah, but if you have a multi-shaft system, it's always going to be the high pressure system because this is a core engine. Yeah, okay. And then we have a certain start sequence. First, the starter starts to turn the high pressure system. Then ignition will be set on. Then after this, we have high pressurized fuel, and in best case, then we have the flame on, light on, you name it as you want, and and the N2 will now start to recreate itself to gain some dynamic pressure. The turbine will transfer part of this in mechanical movement, which is RPM. So by this, yeah, at a certain moment, the system will reach its self-sustaining speed. In order to be on the safe side, the starter will still support, yeah, and then will be disengaged by the disengagement clutch, which is mainly used by those flea weights, and then the starter can make a rest. Yeah, unfortunately, there are 3 reasons for wrong starts, for failures. We talk about hung start, wet start, and hot start. And of course, you know what it means. Yeah, especially hot start and wet start are self-explaining. Hot start, you exceed the given maximum EGT. Wet start, you have no flame on, no light on, no rising or arising of the EGT because you have no ignition. And hung start means that the engine is not able to enhance the RPM by itself. If you remember the video I showed you from the V25 engine, we stood about, I think the engine was about 25, 27%. It was not able to enhance, yeah, the RPM. In this case, if it's that low, for example, maybe the pressurized air is not pressurized enough and has not the power to support the N2 system. One moment. Did you listen carefully what I said? Hello?
We hope. We hope.
Yeah, I hope too. So if you listen very carefully, that should be enough. Yeah. So again, yeah, when the cockpit demands takeoff, the thrust lever has to be moved beyond the thrust set. Yeah. And yes, yeah, fuel flow must be enhanced to gain the thrust, but yeah, as fast as possible, the enhancement of fuel flow, but without touching or coming closer to the stall surge line. You have this graph in your mind, please. Yeah, there will be a steady curve, but there will be a gap, yeah, between the dangerous zone, let me call it this way, yeah, which is the surge line. Yes. Oh, I'm convinced that you are well prepared. As long as you listened and make some notes, whatever. Are you still there? Hello.
Yes, yes, thank you very much.
Okay, then I would say I don't have to wish you luck because you are the smartest group I ever had, you guys from Air Astana. So, but anyhow, that would be enough for today, except you have some questions. Will you all come over here when you come over in February or in March? Let me see.
Yeah, on 5th February.
Oh, let me see here. 5th of February? No. Wasn't it later?
No, exams will be on 5th February.
Okay. Well, because I have, sorry, No Sultan told me, and I make a note here, 25th of March. Is this not valid anymore? That's a pity. I thought I meet you there.
I don't know why.
Okay. Yeah, maybe it has changed or whatever. Yeah. So, and when will you have your exam here from module 14?
Exams will be on 5th February.
The exam will be on 5th of February. Okay, now I got it. Yeah. So,
Yeah.
Which is next week. Yes, it's next week.
Yes.
Yeah.
Next week. Yeah.
Yes.
Okay. So, yeah. Have success. Yeah. And if you do not have any questions anymore, I'm finished. I think I have told you the most important things. From my perspective, the most important things. And since you know mod engines anyhow, so we made this N15 already. So sometimes it's a little bit stupid, whatever. But yeah, if you feel comfortable, if you feel that it's enough, then I would say have a nice rest of the evening. Yeah, you still have some time. And of course, we did not stop yet now. Yeah, we made very long into the evening. Guys, do you have an opinion? Let me know. Yeah. Most important thing that is you have the good feeling that if you have no further questions, yeah, we are through. Yeah, we did it.
Yeah, I think we will do it.
Yeah.
Thank you very much.
Cool. Yeah, no problem. Yeah. And if someone should ask you, we have done until 8 p.m. whatever.
Yeah.
No. Yes.
Okay.
Yeah. Good. Guys, have success. Good luck. Yeah. And maybe we meet when you come here to Gilching someday, somewhere, whatever. And maybe I come over. I think maybe in September, stuff like this. Yeah. Thank you for listening.
Yeah.
Thank you for making your notes, and thank you for not failing, for passing the exam. Yeah. Thank you for this. And have a nice day. Yeah. Or evening.
Have a nice
sorry.
day.
Yeah. Thank you.
Thank you very
Bye.
much.
Thank you very much.
Thank you.
Thank you.